Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. Today we will be discussing about atoms in external fields under the paper Atomic, Molecular and Laser Spectroscopy. After completing the contents, we will be able to understand Zeeman effect, Paschen-Black effect, the Stark effect, and the comparison of Stark effect and anomalous Zeeman effect as well. Zeeman effect. Zeeman effect is named after the great scientist Peter Zeeman, who in 1876 observed that when a light source is brought into magnetic field, each spectral line is split into number of components. This implies that the energy levels of the atom, those are involved in the transition in the presence of a magnetic field, must split into several components. Thus, the interaction of the electronic magnetic moment of the atom with the magnetic field results in splitting. It is known that the ratio of magnetic and mechanical moment of an electron in an orbit is mu L upon L is equal to E upon 2 me with minus sign is equal to minus 2 pi G1 upon H Be. Also, the electron has orbital angular momentum L and a spin angular momentum S. The ratio of magnetic and mechanical moment for the spinning electron is mu s upon S is equal to minus twice E upon 2 me is equal to minus 2 pi Gs Be upon H. Coming to LS coupling, it is assumed that the interaction between the spin angular momentum of the electrons on one hand, the interaction between their orbital motions on the other hand is large compared with the interaction between spin and orbital angular momenta of each electron, and thus LS coupling holds. In case of atom, those have more than one valence electron. The magnetic moment mu L is minus 2 E upon 2 me L, L being the total orbital angular momentum of all electrons. The magnetic moment mu s is then equal to minus 2 E upon 2 me s. Here s is the total spin angular momentum. The vector L and S precess together around their resultant J in the absence of a magnetic field, as has been shown in the figure. When a magnetic field B is applied, L and S couple with it, and in the absence of coupling between L and S, the latter precess independently around B. However, energy corresponding to coupling of L and S with B is smaller than the spin orbit interaction energy in weak field. Thus, B does not disturb the coupling between L and S under such condition. The L and S precess about their resultant J. Because of torque, J precesses around B at a rate small compared with the precession rate of L and S about J. The figure depicts the precession of J about the field direction Z in a weak magnetic field B. The total electronic magnetic moment mu is equal to mu L plus mu S of the atom is not oriented in the same direction as the total angular momentum. J is equal to L plus S. This is because of different dependencies of mu L and mu S on L and S respectively. The figure illustrates vectors L, S and J and the associated magnetic moment vectors. As L and S precess rapidly about J, mu L and mu S precess rapidly as well, resulting mu to 0, and the component parallel to minus J remains a constant in magnitude denoted by mu J. The component of mu along J axis from the above figure is mu J is equal to mu L cos theta plus mu S cos phi, where J is equal to L plus S or S is equal to J minus L. So S square is equal to J minus L dot J plus L, which is equal to J square plus L square minus 2JL. Now 2JL cos theta is equal to J square plus L square minus S square, deducing cos theta is equal to L square plus J square minus S square upon 2JL. Similarly, one can write down cos phi is equal to L square plus J square minus S square upon 2JS. Therefore, mu j is equal to mu L j square plus L square minus S square upon 2jL plus mu S into j square plus S square minus L square upon 2jS. Substituting the values of mu L and mu S, one gets mu j is equal to minus 2me j square plus L square minus S square upon 2j plus 2 into j square plus S square minus L square upon 2j, and further a little of the mathematics will give you the result minus e upon 2me j into 1 plus j square plus S square minus L square upon 2j square is equal to minus g e upon 2me j, where this g is equal to 1 plus j square plus S square minus L square upon 2j square is equal to 1 plus j into j plus 1 plus S into S plus 1 minus L into L plus 1 upon 2j into j plus 1, and this g is called the Landé's separating factor. JJ coupling. In case where interaction between spin and orbital motion of the electron is large compared with the interaction between the spin angular momenta of the electrons on one hand and the interaction between their orbital motions on the other hand, JJ coupling holds, and hence the S and L of each electron are coupled together to form their own resultant J, as has been shown in the figure. The figure presents the vector model for JJ coupling in a weak magnetic field. J1 and J2 couples together to form the resultant. This clearly mentions that the magnetic field lifts the degeneracy, giving rise to 2J plus 1 equidistant sublevels. Those are called Zeeman sublevels. The distance between two consecutive sublevels is G beta E B. Let E naught is the energy of the atom without magnetic field, and then the energy in the magnetic field is given by E is equal to E naught plus G beta E M B. It is known that there is a relationship between term T and energy E, as T is equal to minus E upon Hc. The interaction energy in wave numbers become delta E upon Hc is equal to minus delta T is equal to G beta E upon Hc MB, and minus delta T is equal to G ML, where L is equal to beta. B upon Sc is called Lorentz unit and its value is 0.4678 B centimeter inverse, where B is measured in Webers per square meter, or we call it as Tesla. The separation between two neighboring sublevels is GL and is determined by magnetic field B and G factor belonging to the energy level. The magnetic moment for the two electrons mu j is equal to minus 2 minus E upon 2 me j 1 plus j square plus S square minus L square upon 2j square is equal to minus G E upon 2 me j r. Mu j1 is equal to minus G1 E upon 2 me j1, mu j2 is equal to minus G2 E upon 2 me j1, where G1 and G2 can be obtained from the above equation of G factors. G1 is equal to 1 plus J1 square plus S1 square minus L1 square upon 2J2 square, and G2 is equal to 1 plus J2 square plus S2 square minus L2 square upon 2J2 square, where mu j is obtained from the projection of J1 and J2 on J, and mu j is equal to mu j1 cos of J1j plus mu j2 cos of J2j is equal to minus G1 J1 cos of J1j plus G2 J2 cos of J2j into E upon 2 me. But mu j is equal to minus G E upon 2 me j. On comparing the two equations, one gets Gj is equal to G1 J1 cos J1j plus G2 J2 cos J2j. The angles between J1, J2 and J are constant, and J is equal to J1 plus J2 or J minus J1 is equal to J2, and taking the dot product of J2 with J2, you get J2 square is equal to J square plus J1 square minus 2J J1 is equal to J square plus J1 square minus 2J1J cos J1J, where cos J1J is equal to J square plus J1 square minus J2 square upon 2J1J. Similarly, cos J2J is equal to J square plus J2 square minus J1 square upon 2J2J. Here we need to take into consideration whether we are writing the small j or the capital J. Substituting G is equal to G1 J square plus J1 square minus J2 square upon 2J square plus G2 J square plus J2 square minus J1 square upon 2J square. The magnetic interaction energy resulting from the interaction between the electronic magnetic moment of the atom and an external magnetic field B directed along the z-axis is delta E is equal to minus mu J dot B. Here G is chosen depending whether the coupling is LS or JJ. J cos JB is the projection of J on that is equal to J2. The allowed values for the J along the z-axis are mh cross, m being the magnetic quantum number, and takes values from plus J to minus J, a total of 2J plus values. So delta E is equal to G EH upon 4 pi ME MB is equal to G BE MB, where this BE is equal to EH upon 4 pi ME. Past and back effect. In describing the anomalous Zeeman effect, it is assumed that external magnetic field is weak compared to the internal fields. Consequently, the interaction between J and H is weak compared to the interaction of orbital and spin magnetic fields. The interaction between L and S starts loosening or gets broken at sufficiently large value if the strength of the external magnetic field is increased to the extent that it starts competing with the internal field. Under this condition, J starts losing its significance and L and S interact independently with the external magnetic field, resulting in the independent precessions of L and S about J. Their precession is much faster than the precession of residual interaction of L and S about J. Precesses slowly around H in comparison to LA and S about J. This is known as past and back effect. The separation between the spin components or between the Zeeman components is a measure of the corresponding precessional frequency. In the anomalous Zeeman effect, the precession of L and S about J is faster, and therefore the average values of their components normal to J are assumed as 0 in order to avoid the perturbation of other precessions. However, when the external magnetic field is of the same order as that of the internal fields, the case is different, and the relation minus T is equal to G L M J no longer holds good. Further, J and S will precess independently about H as the field is increased, and hence will become quantized independently in the direction of field H. The figure depicts the precession of L and S about external magnetic field H and their space quantization. The projection on H takes integral values ML is equal to plus L, L minus 1, 0, minus 1, and so on, due to which there are 2L plus 1 values of ML for a given value of L. The projection of S on H takes two values, MS is equal to plus minus 1 by 2, minus delta T is equal to G L M J. The figure is self-explanatory, giving various values of ML and MS, and also showing the precession of L and S. Now consider the transition between 2d phi by 2 and 2p 3 by 2, and using the G value from the equation 1 plus J square plus S square minus L square upon 2J square is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 upon 2J into J plus 1. The G values of 2d phi by 2 and 2p 3 by 2 are 4 by 5 and 4 by 3 respectively. The splitting of the levels and the allowed transitions have been shown in the figure. Corresponding to 2p 3 by 2 and corresponding to 2d phi by 2, the levels have been shown in the figure. The allowed transitions, that is weak field Zeeman splitting. The allowed selection rules for transition between magnetic subshelves are delta M is equal to 0, that is P component or the pi component, delta M is equal to plus minus 1, that is S component or the sigma component, and delta J is equal to 0 with M is equal to 0, means M is equal to 0 is not allowed, and the 2D 5 by 2 to 2P 3 by 2 transition splits up into 12 components. That means 4 P components and 7 components, total of 12 components. As an example, further consider the transition between 1F3 to 1D2. As 1F3 to 1D2 are singlet, therefore their G values are equal to 1, and the figure shows the splitting of the levels in weak magnetic field and allowed transition between them. The allowed transitions from 1F3 to 1D2 in weak magnetic field are shown in the figure. Further elaborating, there are only 3 distinct energies at A plus A and A minus A. Thus, the spectral line corresponding to 1F3 to 1D2 transition splits into 3 components in weak magnetic field, one at the same position and other 2 are displaced on either side of the undisplaced line. Now it is clear that when levels involved in a transition are singlet, only 3 lines are observed, corresponding to normal Zeeman effect. The table very well shows the allowed transitions in weak magnetic field. Along the horizontal, M of the initial states is shown, and along the vertical, M of the final state is shown. And if the levels in a transition involved are different from singlet, one gets the anomalous Zeeman effect. And conclusively, when the contribution of spin towards magnetic moment is 0, the normal Zeeman effect is observed and the spin contribution is taken into account, then anomalous Zeeman effect is observed. Representation of transitions between Zeeman sublevels on a normal energy level diagram can be understood with the following arrangement. Writing in a row all the values of M for transition 3P 3 by 2 to 2S by 2 transition. Below each value of M, put the displacement mg of the magnetic level of the initial spectral line. Similarly, write down the displacement of the levels belonging to final term in the next row. The vertical arrows represent the transitions. M is equal to 0, that means pi or P. Forbidden transition is represented by arrows of greater inclination. The line positions are expressed as multiples of 1 by R, where R is called the Runge denominator and is the least common multiple of the denominator in the values of mg. The usual notation for a Zeeman pattern consists of a long line with Runge denominator beneath it with integer above it to show at what multiple of 1 by R the components lie. The table demonstrates the procedure for obtaining the Zeeman pattern for 2P 3 by 2 to 2S 1 by 2 transition. The G values for 2P 3 by 2 and 2S by 1 by 2 are 4 by 3 and 2 respectively. The vertical differences P component are 3 by 6 and minus 3 by 6, while the diagonal difference or the S component are 6 by 6, 5 by 6, minus 5 by 6 and minus 6 by 6. The Runge notation, it is written as delta nu bar is equal to plus minus 3 plus minus 5 plus minus 6 divided by 6 into L centimeter inverse, with 2 P components being set in parentheses followed by the 4 S components. Further, coming to the intensity rules, the intensities of the components of one line are symmetrical relative to the position of the original line. The sum of the intensities of the combinations of a level characterized by a magnetic quantum number M with level M minus 1, M and M plus 1 is independent of M. Sum of the intensities of all P components is equal to the sum of the intensities of all S components, and the table presents the intensity rules as described. When Zeeman effect is observed in a direction perpendicular to the magnetic field, only half of the intensity of the S component is observed. The other half is observed in a direction parallel to the magnetic field. Therefore, in studying intensities, S components need to be multiplied by 2. A and B are constants in the above table that need not to be determined for relative intensities within each Zeeman pattern. The table holds for any coupling scheme. To determine the strongest component, the following approximate rule is useful. In case where J1, J2, the vertical differences in the middle of the scheme and diagonal differences at the ends give respectively the strongest P and S components. If J1 is equal to J2, the vertical differences at the end of the scheme and the diagonal differences at the center give respectively the strongest P and S components, with the restriction that M is equal to 0 and M is equal to 0 is forbidden. There are polarization rules as well, corresponding to viewed perpendicular to the field or viewed parallel to the field. In case these are viewed perpendicular to the field, delta M is equal to plus minus 1, plane polarized perpendicular to B, you get S or sigma component, and delta M is equal to 0, plane polarized parallel to B, P or pi component. Delta M is equal to plus minus 1, circularly polarized S or sigma component, and delta M is equal to 0, forbidden, that means P or pi component. There are certain things to note, as it is noteworthy that weak or strong external magnetic field is not in absolute term but is in relative to the net internal. A weak external field for one atom could be strong for some other atom. Magnetic field of 30 kilogauss produces Siemens separation of 2 cm inverse in sodium, while the LS interaction yields J1 by 2 and J3 by 2 with a separation of 17.8 cm inverse, which is a measure of internal field, indicating that internal field is much stronger than the external field. On the other hand, same magnetic field applied to H atom, hydrogen atom, Siemens separation measure of external field is much larger than the LS interaction separation, which is a measure of internal field, that is less than half a wave number. Thus, the field which is weak in case of sodium is strong for hydrogen atom. The Stark effect. When a square of light is placed in an electric field, the spectral lines split up into number of components. The Stark effect is due to the interaction between the electric movement of the atom and the external electric field. The term to the interaction energy is W is equal to minus P into E. Here P is the electric dipole moment and E is the external field. Electric dipole moment in atoms arises as a consequence of the way that charge is distributed within the atoms. There exist two aspects of Stark effect. One is linear effect and the other is quadratic effect. The linear effect is due to the dipole moment that arises from a naturally occurring non-symmetric distribution of electron charge, while the quadratic effect is due to a dipole moment that is induced by the external field. For simplicity, the effects of fine and hyperfine structure are ignored. Linear Stark effect. In the figure, the transition from the ground level n is equal to 1 to first excited level n is equal to 2 of atomic hydrogen is the simplest case of the linear effect, wherein the excited level splits into 3 equally spaced sublevels under the influence of the external field. The spacing between sublevels increases linearly with the applied field. The central sublevels of n is equal to 2 and the ground level do not shift in response to the field. And it is again to note that as a general case, n level splits into 2n minus 1 sublevels that separate in the field at a rate that scales with n. Thus, the higher n states are more sensitive to the external fields. As a linear effect is the result of the interaction between the electric dipole moment due to the distribution of charge within the atom and the external field, the dipole moment can be understood by considering an eccentric elliptical orbit. The nucleus is at one focus and the electron follows a Kepler orbit that sweeps out equal areas in equal time. The electron moves fastly when it is near the nucleus and slowly when it is far from the nucleus, and as a result, the electron's position averaged over an orbit is not centered on the nucleus. The separation between positive and negative charge carriers are referred to as dipole moment. The size of the naturally occurring dipole moment corresponding to a highly eccentric orbit that can be estimated given that the mean radius of an atom in a state of principal quantum number n is on the order of n to a theta, where a theta is Bohr radius. Thus, the dipole moment, which is the product of charge and the charge separation, is En to a theta. This estimate is comparable with the observed moment of the Stark level, 3 En minus 1 a naught by 2. So W is equal to 3 by 2 Enkao, and K is called the electric quantum number that ranges from plus n minus m minus 1 to minus n minus 1 minus m for all possible values of m, that is from plus n minus 1 to minus n minus 1. So K plus minus 1 that have the smallest dipole moments corresponding to circular orbits. As each of the electrons take each of the two values of m, there are 2 into 2l plus 1 different quantum states, each corresponding to different combination of quantum numbers. The figure depicts space quantization for L is equal to 1 and S is equal to 1 by 2. When the LS interaction is significantly loosened or broken, major part of the total energy of the atom consists of the energies due to the precession of L around B plus energy due to precession of S about B. Thus, the major energy shift is delta E is equal to delta E LH plus delta E S B is equal to B mu L plus B mu S is equal to B mu L cos of L B plus B mu S S B. Using equations for mu L and mu S respectively and substituting the values of cos LB and cos SB, the equation is reduced to delta E due to magnetic energy is equal to B ml plus 2ms EB upon 2mc is equal to B mu B ml plus 2ms. Mu B is Bohr magneton. In terms of wave numbers, minus delta T is equal to ml plus 2ms into L. Though L and S precess independently, but each produces magnetic field on the electron, causing some perturbation to others' motion. Though the LS interaction is small compared to the effect of the external magnetic field, but need to be taken into consideration. The separation due to this residual interaction is of the same order of magnitude as the field-free fine structure doublet separations. Therefore, using the equation which has been written for term minus delta T is equal to ml plus 2ms into L, and the J is vector sum of L and S. Its contribution can be written as delta T Ls with minus sign is equal to alpha Ls cos of Ls, where alpha is equal to R alpha square z raised to the power 4 upon n cube L plus 1 by 2 L plus 1. In field-free LS interaction, L and S rotate together as a rigid system about J. Thereby, the angle between L and S is constant, rendering easy evaluation of cos of Ls. In the present case, angle between L and S is varying continuously because of the anomalous behavior of spin. S precesses faster than L. This necessitates the use of average value of cos Ls that can be evaluated using trigonometry theorem, writing cos Ls is equal to cos Lb in cross cos Sb. Using this theorem along with the values of cos Lb and cos Sb from the figure, one finds delta T Ls is equal to A L ml upon L dot S ms upon S, and adding this to the equation of total energy shift, minus delta Ls is equal to A L ml upon L S ms upon S, and adding this to the total energy shift equation, minus delta T is equal to ml plus 2ms L plus A ml ms, and a general relation for the term values is written as T is equal to T naught minus ml plus 2ms L minus A ml ms. T0 is the term value of the hypothetical center of gravity of the fine structure doublet. As J is no longer well-defined quantum number, Therefore, past and back effect is described in terms of quantum number ml plus 2 ms. So, summarizing all these, what we have learnt is the Zeeman and Stark effects referred respectively are due to the effects of external magnetic and external electric fields on the structure of atoms or molecules. The effects are observed through the modification of spectral features such as strength, polarization, width, and position of emission or absorption lines. The structure of anomalous effect is more complicated than that of the normal effect. The field dependence is also more complicated. In weak fields, the levels separate linearly with the strength of the applied field as they did for the normal effect. However, the rates of separation of levels are different than those observed for the normal effect. In moderate fields, the levels shift in a complicated way that is not easily described by any simple power law. In strong fields, the levels again shift in proportion to the field strength, but this time with rate of separation that are the same as that of the normal effect. The anomalous effect was a mystery until 1925 when Goudsmit and Ollenbach introduced the concept to electron spin. Electron spin was conceived to explain why the fine structure separation of the 2p levels of alkali metal atoms were so much large than the corresponding levels of the hydrogen. Goudsmit and Ollenbach suggested that electrons have both an intrinsic angular momentum and an intrinsic magnetic moment. Following this assumption, the fine structure separating was shown to be the result of the magnetic interaction between the intrinsic magnetic moment of the electron and an internal magnetic field produced by the electron's orbital motion. Thank you.